Okay, we're going to continue in this video looking at velocity and in one direction, one-dimensional motion. And I like this example problem because it requires a little bit of thinking. You sort of have to take a step-by-step process, and some students leap to an incorrect conclusion, and so we'll show why that's incorrect with the math. So the problem here says that a car travels at a constant 50 kilometers per hour for 100 kilometers. It then speeds up to 100 kilometers per hour, so it doubles its speed, and drives for another 100 kilometers. What is the car's average speed for the 200 kilometer trip? So here's what a lot of students might think. They think, well, for the first half, you're going 50. For the second half, you're going 100. The average of 50 and 100 is 75. So the answer is 75 kilometers per hour. That's the average speed. But that is not correct. That is not really taking into account the definition of velocity and working it through. So let's see what happens when we do that. So let's first kind of write out our knowns. Well, we have them written out. Let's look at them. Average velocity 1 is 50 kilometers per hour. So we'll write that out using our abbreviations. V sub 1. We use subscripts a lot in this class to denote initial, final, for different bodies. If we're talking about like collisions between body A and body B. So get used to that, seeing subscripts. So average, the bar overhead means average. Average velocity 1 equals 50 kilometers per hour. Delta, change in position 1, is 100 kilometers per hour. So if we started at some origin on an xy axis with a value of 0, we traveled in the x direction 100 kilometers to get to this point. Okay, and then we're going to travel for another 100 kilometers to get to the next point. So the delta x1 is 100, and delta x2, the second change in distance, is also 100. Okay, and what changes is the velocity. Average velocity 2 is 100 kilometers per hour. So we've increased from 50 to 100. Okay, so velocity, if we look at the definition of average velocity is delta x over delta t. Okay, we know the change in x. We know how far we traveled. We know how fast we were going. What we don't know is how long it took us. Okay, so we're just looking at the first part of the trip now. So v1, x1, t1. So we want to solve this equation for this variable. So we rearrange it algebraically, and we get delta t1 is equal to delta x1 over delta v1. Okay, what was our delta x1? Our delta x1, our change in distance, was 100 kilometers. How fast were we going in the first part of the trip? We were going at 50 kilometers per hour. So if we take 100 divided by 50, that is 2. Okay, so this is one of these situations where, again, the author has a tendency to do this. Use these round numbers like 50 and 100. Okay, and then we have to ask ourselves, is this 0 significant or not? According to our rules of significant figures, it is not. Okay, technically this only has one significant figure. But based on my experience of reading through the example problems in the textbook, I believe the author intends for this to be a 2 significant figure number. I know that seems a bit confusing and contradicts what we've said before about significant figures, but for now we will assume that this is two significant figures, that he really meant to say like 5.0 times 10 to the first kilometers per hour. That's what he really should have said, but he didn't. He just put 50. Okay, so assuming that he did that, then we'd have two significant figures. The kilometers and kilometers are going to cancel each other out, and when we flip this up to the top, it goes from the bottom of the fraction to the top, and we're talking 2.0 hours. So for the first part of our trip, that's how long it took us. We traveled at that initial rate of velocity for 2 hours. Let's look at the second part of the trip. Okay, so again, delta t is going to be equal to delta x over delta v. So I should put 2 subscripts on these because we're representing the second part of our trip. So the distance traveled in the second part of the trip is also 100 kilometers, except this time we were traveling at 100 kilometers per hour. So that is 1.0 hours. So that's the time it took us for the second part of the trip. So in total, our total time, and I can put a little total subscript down there, is 2.0 plus 1.0 is 3.0 hours. That's how much time the entire trip took. And the distance traveled, the total distance traveled, was 100 plus 100 kilometers is 200 kilometers. So if we then find the average velocity for the total trip, that's going to be equal to our delta x divided by delta t. Delta x was 200 kilometers. Delta t is 3 hours. So we divide 200 by 3 and get 67 kilometers per hour is the average. So if your initial thought was, oh, the average velocity is 75, well, that's not correct. It's 67. And again, an argument could be made that this really should only be to one significant figure. So you might even round this to 70 kilometers per hour. Now, I just happen to believe the intention of the author was for this 50 to be exactly 50. So we've been talking about average velocity with a little bar over it indicating the average velocity is delta x over delta t, the change in position divided by the change in time. Okay, but think about your commute to school. You get in the car and you drive. You're not driving at exactly the same speed the entire way. You could find your average velocity by taking the distance between your house and the school divided by the amount of time it takes you to get there. But throughout your trip, you're accelerating, you're decelerating. Sometimes you're at a stop. If you get on the highway, you're traveling a lot faster than if you're just driving on back roads. So the distinction here is we have average velocity with the bar over it. Without the bar is instantaneous velocity. So instantaneous velocity is if we look at a split second, and it's represented here mathematically by a limit as delta t approaches 0. So this is basically a fancy mathematical way of saying delta t gets really, really small. It approaches 0. It doesn't actually become 0 because you can't divide by 0. It just becomes something really, really tiny. So if we look at just a split second, an instant, how fast are you going at that particular instant. So we are not going to need to necessarily worry about limits or doing anything with limits mathematically, but you need to understand conceptually that an instantaneous velocity is looking at how fast something is traveling at a single point in time rather than the average over a period of time. So the tortoise and the hare is a great example of the difference between average and instantaneous velocity. The hare obviously has much higher instantaneous velocity, but if it comes to a rest and the tortoise, which has a lower instantaneous velocity but maintains a higher average velocity over the course of the race, actually ends up winning. So I've mentioned acceleration. Let's formally define it, what it is. So average acceleration is going to be our change in velocity over time. So it's going to be equal to delta V over delta T. Okay, so we're changing our velocity over some period of time. Oftentimes we associate acceleration with automobiles, with high-performance sports cars. We want to know what their 0 to 60 time is. How quickly do they accelerate? Okay, so that's how quickly do we change velocity in the context of 0 to 60. We're talking about 0 miles per hour to 60 miles per hour in some given period of time. Let's look at a specific example problem here. If we have a car that's accelerating on a straight road from rest, so rest means that the initial velocity 1, is 0, to 75 kilometers per hour. So our velocity 2 is 75 kilometers per hour. What is the magnitude of its average acceleration? Okay, so acceleration is going to be delta V over delta T. So our final, that's going to be V2 minus V1 over delta T. Our final velocity was 75. Our initial was 0. And the time was 5.0 seconds. So that's going to give us 15, but we need to pay attention to our units. This was 75 kilometers per hour, and this was kilometers per hour. Kilometers. So we have kilometers per hour per second. Well, that's a weird unit to report answers in. We don't like to do that, to have two different units of time stacked on top of each other. So what we really need to do is convert our 15 kilometers per hour to meters per second is really the preferred units that we're going to use. So if we take our 15 kilometers per hour, we want to get rid of kilometers. So I'll put 1 kilometer is equal to 1,000 meters. And I want to get rid of my hours, so I'll put that on top. 1 hour is 3,600 seconds. And if I multiply that out, I get 4.2 meters per second. So my acceleration is equal to 4.2 meters per second, or we write that as 4.2 meters per second squared. Okay, so those are our units of acceleration, meters per second squared. So the acceleration of this car was 4.2 meters per second squared, and it looks like I'm just about out of time. So We'll resume this discussion in the next video.